In this video, we discuss logarithmic differentiation. It's a differentiation technique that makes it easier to evaluate derivatives of products, quotients, and powers of functions. And it also uses properties of logarithms, or it's based on properties of logarithms. So these are the three important properties that we need in order to use logarithmic differentiation to compute derivatives relatively simply. I wanted to derive these for you in this video, so we'll do the derivation of these formulas, and then after we do the derivation of the formulas, then we will apply them in the process of logarithmic differentiation. So let's say we need a couple of things. We're dealing with logs of products, logs of quotients, and logs of powers. And in order to do that, these expressions inside the parentheses of the logarithm, they have to be positive. So let's let A and B be positive, or assume A and B are positive so that the logarithms are well defined. And let's say that the log of A is equal to X and the log of B is equal to Y. Now these identities, these properties, are true for any base. And when there's no base listed here, it's an implied 10. So this would be log base 10 of A to the n equals n times log base 10 of A. But technically these could be any log. So I'm going to write log base A of A to the n equals n times log base A of A. I'm using capital A inside the parentheses and lowercase a for my base. I'm going to use lowercase a there and there and there and there and there and there. So this will work for any base. I will tend to list the properties of logarithms using log base 10 or the natural log. Either one is fine. But technically these work for any base A, where A is a non-negative number, or excuse me, a positive number, not equal to 1. So we've got this. Now, just as a reminder, if somebody asks you for the log base A of X, the answer is Y if the following is true, if A to the Y power equals X. So you can almost think of a logarithm as asking you a question. If somebody says, what is the log base A of X? They're saying, X to what power? Or excuse me, A to what power? Is X. So they're saying, okay, if I take A and I raise it to some power, what does X have to be? Or excuse me, if I take A and I raise it to some power and I get X, what does that power have to be? So here's an example. If somebody gave you log base 2 of, let's say 32, and they asked you to evaluate that, well, the answer is going to be some number. And you'll say, well, what number is that? It's the number that answers this question. 2 to what power is 32? And if you said the fifth power, you're right, because 2 times 2 is 4, times 2 is 8, times 2 is 16, and then if you multiply by 2 a fifth time, you get 32. So since 2 to the fifth is 32, log base 2 of 32 is 5. So 2 to this power is this number. So when I see A, or log base A of X, I think A to what power is X? So I'm almost putting that little box there and saying, well, what has to go in that little box so that this equation is true? And then that is the answer for my logarithm. So we're keeping that in mind. So we're going to prove these properties of logarithms now. So we're going to assume A and B are positive, and log base A of capital A is X, and log base A of capital B is Y. Well, then by definition, lowercase a to the X is equal to A, and lowercase a to the Y is equal to B. So with that in mind, we'll start with this second property. Let's say somebody asks us to evaluate log base A of A times B. Well, since A is A to the X and B is A to the Y, this is log base A of A to the X times A to the Y. Well, because of our exponent properties, we can add those exponents. This is log base A of A to the X plus Y. And then we're asking ourselves here, Well, a to what power is a to the x plus y? Well, the x plus y power, right? And then we say, well, what is x? Well, x is log base a of a. And what is y? Well, y was log base a of b. So log base a of a times b is log base a of a plus log base a of b. This is the property that we'll use, but it's based on these exponent properties. So the corresponding exponent property is this: a to the x times a to the y equals a to the x plus y. It's because that this is true that this is true. Because if my a is, or if the log base a of a is x, and that's equal to that, and the log base a of b is equal to y, which implies that a to the y equals b, then we can rewrite this way, and then we have the logarithm undoing the exponential, the corresponding exponential, and we just get that x plus y back. Okay, so we know that log base a of a times b is log base a of a plus log base a of b. I want to take that and I want to, let's look at the quotient one next. I've got log base a of a divided by b. Well, a and b can be written in terms of our base as log base a of a to the x divided by a to the y. I've got an exponent property for that. A to the x divided by a to the y is a to the x minus y. And then you say to yourself, okay, a to what power gives us a to the x minus y? Well, obviously the x minus y power. And then you say, well, what was x? X was log base a of a. You say, well, what was y? Y was log base a of b. So the log of a quotient, is the log of the numerator minus the log of the denominator. And that's because of this property. Now for log base a of a to the n, there are a couple of different ways you can think about it. You can think about that using log properties if you want to. A is a to the x. So this is a to the x in parentheses raised to the n. If I take a to the x and I raise it to a power, we just multiply those two exponents together. So this is a to the x times n. And then you say the log base a of a to the x times n is, well, the answer to this question. A to what power equals a to the x times n? Well, e to the x times n power, of course. N is from our original expression, and this x was log base a of capital A. So if you have log base a of some power, you can bring that power out front, and you'll have that power times log base a of a. Now, another way you can think of this, this raising something to the nth power is repeated addition. So if you didn't like this proof because you're not comfortable with this identity or something like that, you could say, let's apply this log base a of a product where instead of having a times b, we've got a times a. If I had a times a here, this would be a to the x times a to the x, which would be a to the 2x, right? So I'd have 2x here. And you could think of that as 2 times log base a of x if you wanted to. Or you could just think of that as log base a of a plus another log base a of a. So how many of them do you have? You have 2 of them. So that's another option. So just using that first property repeatedly, the log of a product is the log of the first factor plus the log of the second. So I've got 2 of those there. What if I had log of a cubed? That's going to be log of a squared times a. So we'll have log of the first factor plus log of the second factor. But the log of the first factor, as the log of a squared, was 2 times log of a. So now I've got 3 of them. So if we continue in this way, if I've got like log of a to the 5th, well, I could write that as log base a of a to the 4th times an extra a. So I'd have log base a of a to the 4th plus log base a of a. And then you'd say, well, what was log base a of a to the 4th? Well, I'm pretty sure it's just going to be 4 times log base a of a. We see this pattern. If I've got a log base a of a squared, I get 2 times log of a. Log base a of a cubed, I get 3 times log of a. If we did log base a of a to the 4th, I'm going to factor that a to the 4th as a cubed times a. I'm using a cubed times a because I already know the log of a cubed. This is log base a of a cubed plus log base a of a. And log base a of a is 3 times log base a of a. And because I multiplied by an extra a, I get another one. So there are 4 of those. So we can repeat this pattern and say, well, what's the relationship between that exponent there and the coefficient? Well, they're always the same. Log base a of a cubed is 3 times log base a of a. The log base a of a to the 4th is 4 times log base a of a. I keep saying a of a. I know that's a little bit annoying. But of course, we're talking about capital A here and lowercase a here. Those are 2 different numbers. But in general, we're going to end up with an n out front, which is the same result that we get if we do it this way, using this exponent property. A to the x raised to the n is a to the x times n. Log base a of a to the x is asking us a question. A to what power is a to the x times n? Well, it's the x times n power, of course. And then n we just bring down, and x was log base a of a by definition. So that's another way we can prove it. So let's just practice that a little bit. So let's say somebody asks you for the log base 2 of 8 times x. Well, since that's a log of a product, I could write that as log base 2 of 8 plus log base 2 of x. And then for this, I'd ask myself the question, 2 to what power equals 8? The 3rd power, right? So this must be 3 plus log base 2 of x. Or let's say we've got log base, or just log of 10,000 divided by x to the 5th. Well, that, by the quotient rule for logarithms, this log property, the log of a quotient is the log of the numerator minus the log of the denominator. So we're going to have log of 10,000 minus log of x to the 5th. And then we say, okay, well, what is 10,000? Well, remember, whenever there's no subscript here, the implied base is 10. So I'd like to write this 10,000 as a power of 10, since it has 4 zeros. That's 10 to the 4th. So I say 10 to what power is 10 to the 4th? Obviously the 4th power. So we write down our 4. And then here I've got log base 10 of x to the 5th. Since that power is inside, we can use this property. Log base a of a to the n is 5 times log base a of a. So we'll bring the 5 out front, and then we'll have that right there. And let's say I've got natural log of e to the 15th. There are 2 different ways you can think about this. Here with the natural log, the implied base is e. So you can say e to what power is e to the 15th? Obviously the 15th power. Or you can think of that as applying that property. You bring the 15 out front, and then you multiply by log base, or the natural log of e. And you say, well, what's the answer for natural log of e? You're saying e to what power is e? Obviously the 1st power. So that's a 1, and we get 15. But either way, whether you think of it just in terms of the definition of that logarithm, or if you think of it in terms of that property, we'll still get the answer of 15. So here are our properties. These are the ones that we're going to use to simplify expressions before we differentiate them in this process called logarithmic differentiation. So here's an example. And so we're asked to use logarithmic differentiation to evaluate the derivative, or to compute the derivative, or to differentiate. Either way, all of those terms work. So let's say we have y equals x times the square root of x minus 1 cubed, all divided by the square root of x plus 1. Now, before we get started, we should notice that this expression is only defined when x minus 1 is positive, and x minus 1 is positive, when x is greater than 1. This expression is well defined when x plus 1 is positive, which means x is greater than negative 1. So the domain of this function, well, comes from comparing those two domains. One goes from -1 to infinity. The other one goes from +1 to infinity. I want the largest interval where both of these are well defined. And both of these are well defined when x is greater than 1. If x is between -1 and 1, I can substitute that value into this expression. Like I can substitute x equals -0.5 into this, I get the square root of 0.5, which is fine. But if I substitute that 0.5 or -0.5 into this one, we're gonna have a problem. We're gonna end up with a negative under the radical. We'll get complex answers, and that's not what we want. So we're gonna use logarithmic differentiation to evaluate the derivative of this. The implied domain is that x is greater than 1, and this is how we do it. It might say, okay, if I'm taking the derivative of this just traditionally using basic rules, well, I've got a quotient. I have to use the quotient rule to take the derivative. I'm going to say low d high minus high d low over low low. And when we take the derivative of the bottom, we're going to have to use the chain rule because you've got that x plus 1 under the square root. And when we take the derivative of the top, or the numerator, we're going to have to use the product rule with the chain rule. We've got the derivative of a product, and whenever we do the derivative of the second, that requires the chain rule as well. So you see, it's getting increasingly complicated. With logarithmic differentiation, none of that is necessary. All we do with logarithmic differentiation is we say, I've got a quotient that's relatively involved. I'd like to take the derivative of this. I think it'll be easier to take the derivative if I take the logarithm of both sides. So we'll compute the logarithm of both sides. And then we use those log properties. And I'm just going to use natural log here. Natural log of a product, is log of the first factor plus log of the second factor. Natural log of a quotient is log of the first factor minus log of the second factor. And log of a to the n is n times log of a. All right, so on the left-hand side, the right-hand side, I see I've got the log of a quotient. It's almost like you just sort of stand back and squint and you say, what does that look like? It looks like a fraction. So we're going to use this quotient one first. The log of a quotient is log of the numerator minus log of the denominator. Now with the square roots, you probably want to write those as exponents. The nth root of x to the m is x to the m divided by n. So that power on the x, that goes in the numerator, and the index of the root goes in the denominator. Now, whenever you have a square root, there's an implied 2 there. So this is a 2, and that's a 2. And with this x plus 1, it's not raised to any power. So I'm going to think of that as all being raised to the first. With that in mind, we can rewrite that second factor in this expression as this is an x times x minus 1 raised to the 3/2 power. That 3 goes in the numerator for the exponent, and that 2 goes in the denominator. That's a little bit misleading the way it looks right now. It looks like an x squared. Remember that 2 is just something that I added, that I wrote so that the index of the radical was no longer implied. The index of the radical is usually explicitly written there, except for with square roots. With square roots, we just assume it's a 2. Okay, so I've got natural log of x times the quantity x minus 1 raised to the 3/2 minus natural log of the square root of x plus 1, which is the same as x plus 1 to the 1/2 power. This exponent goes in the numerator, that exponent goes in the denominator of that rational exponent. And then you say, okay, for this, you again sort of stand back and squint. What does it look like? It looks like a product, right? I'm multiplying something with something else. So according to the product rule, the log of a product is the log of the first factor plus the log of the second. So we'll have log of x plus log of x minus 1 to the 3/2 power. And I don't really have anything to simplify here now. Now I've got log of something raised to a power, so for that one I can use my power rule. And for this one, I've got log of something raised to a power, so I can use this rule as well. I want to be careful about calling it a product rule, a quotient rule, or a power rule, because those are names that we typically associate with the product rule, quotient rule, and power rule for differentiation. So we'll have a natural log of x here. This is natural log of something raised to the 3/2. So you bring that 3/2 out front. That something still in parentheses inside the logarithm. The negative comes down. And then you want to bring that 1/2 out front in the same way. Now, once you have a sum or a difference inside those parentheses, you cannot simplify that. We do not have a sum rule here. We don't have log of a plus b equals something. That doesn't work. Log of a times b is log of a plus log of b. And again, the reason why that's true is because of these exponent properties. We don't really have a similar property if we had a sum here, because in this case, we're multiplying two exponents together. We're dividing two exponents, and then we're multiplying an exponent by itself repeatedly, because that's what raising something to the n actually means. We don't have like a sum of exponents property. Since we don't have anything like that, that x minus 1, log of x minus 1 can't be simplified, and log of x plus 1 can't be simplified. So now I know that natural log of y is equal to this, and now I'm ready to compute the derivative of this. So what we do with logarithmic differentiation is we simplify, we take the log of both sides. Let's write this down. And you can use any base you want. I usually use the log base n, or log base e, natural log. And then you're going to use log properties to simplify. And you want to simplify as much as possible. You stop when you no longer have any powers, products, or quotients inside the logarithms. And then when you're at this point, you're going to use implicit differentiation to take the derivative. We're going to take the log, or excuse me, the derivative of both sides with respect to x, remembering that y is a function of x. The derivative of the log of some function is 1 divided by that function times the derivative of the inside, which is dy dx by the chain rule. And that's going to be equal to the derivative of log of x. The derivative of log of x, or natural log of x, is 1 over x. And this 3/2 is just a constant. We bring it down. And they say, what's the derivative of natural log of x minus 1? Well, there's an inside function there. The derivative of the log of some function is 1 divided by that function times the derivative of the inside by the chain rule. And the derivative of the inside is a 1. Then we bring the negative 1/2 down, and we see another inside function. That's that x plus 1. You say, well, what's the derivative of log of that function? It's 1 divided by the function times the derivative of the inside by the chain rule. And the derivative of the inside is a 1. Now I'm going to put this in parentheses because I'm going to multiply it by that 2 in a second, that in parentheses as well. So what we have is x minus 1 plus, if I multiply straight across, 3 divided by 2 times x minus 1, minus 1 divided by 2 times x plus 1. And that's equal to 1 over y times dy dx. And we're trying to get dy dx by itself. So dy dx is all of this times y. You would say, okay, well, I don't want my answer in terms of y. I want my answer in terms of x only. Well, what was y? Well, remember what we started with. Y was this expression. So we can replace y with this, and we'll get our final answer in terms of x only. So you have 1 over x plus 3 divided by 2 times the quantity x minus 1 minus 1 divided by 2 times x plus 1. And y is x times the square root of x minus 1 cubed, all divided by the square root of x plus 1. So that's our derivative for all x greater than 1. And that is called logarithmic differentiation. Now, some students might say, I don't want to do that. I'd rather use the quotient rule with the chain rule and the product rule and all that. You could have done that if you wanted to. When you take the derivative of this, you could use the quotient rule and then the chain rule with the chain rule for the derivative of the denominator, the product rule with the chain rule for the derivative of the numerator, and then simplify. It turns out if you do that, you will get an expression that is equivalent to this. If you want to, you could distribute here and try to see what this expression is. Well, if we distribute this to this 1 over x, got that. And then here, if I distribute that expression to the 3 over 2 times x minus 1, got an x times the square root of x minus 1 cubed divided by the square root of x plus 1. And then on the last one, we'd have negative 1 divided by 2 times x plus 1 times our y. So we could simplify this. X divided by x is 1. Now, these expressions involving radicals might be simpler or easier to simplify if I rewrite them with rational exponents. So square root is an implied 2 for the index of the root. This is going to be an x minus 1 to the 3 halves. And then in the denominator, we have x plus 1 to the 1 half. Then if I multiply straight across here, I've got minus 3x times this expression again is x minus 1 to the 3 halves. And then I've got 2 times x minus 1. And then this is x minus 1 to the 1 half, or x plus 1 to the 1 half. And then if we multiply straight across, we've got x times x minus 1 to the 3 halves again, because there's that implied 2 there, all divided by 2 times x plus 1 times x plus 1 to the 1 half power. Okay. Now this can't be simplified, so I'm going to leave it alone. But I notice with this expression, I've got a x minus 1 to the 3 halves in the numerator and x minus 1 to the first in the denominator. If you have something raised to the n divided by something raised to the m, you just subtract the exponents. Since they have the same base, x minus 1 to the 3 halves divided by x minus 1 to the first, it's just x minus 1 to the 3 halves minus 1, or x minus 1 to the 1 half. So I'm just applying this rule. But instead of having an x for my base, I've got an x minus 1 for my base. So that gives me this. X minus 1 to the 3 halves minus 1 is 1 half. And then we've still got that 2 down there. And then we've got an x plus 1 to the 1 half. And then similarly, Here I've got an x plus 1 and an x plus 1 to the 1/2. They have the same base. There's an implied 1 there. So we would add the exponents, just like we do when we use this property. X to the n times x to the n is x to the n plus m. This is going to be x plus 1 to the 1 plus 1/2, which is 3/2. So that's our answer. That's one form of the derivative. I mean, if we wanted, we could get a common denominator. I don't think I will. Well, let's get a common denominator. Because when we use the quotient rule on this, we're probably going to have a common denominator, right? Well, no, let's leave it like this. I don't actually know what it's going to look like. Let's check our answer by using the quotient rule. So we have y equals the derivative, or y prime equals the derivative with respect to x of the quotient. And I'm going to rewrite that x minus 1, or that square root of x minus 1 cubed is x minus 1 to the 3/2 right away. And then the x plus 1 to the 1/2 is in the denominator. So just rewriting first to make it easier to take the derivative of the quotient. Remember, the derivative of the quotient is low d high minus high d low over low low. And that derivative operator applies to what's in front of it. So we're going to have low d high minus high d low. All divided by low low. X plus 1 to the 1/2 times x plus 1 to the 1/2 is x plus 1 to the 1, or x plus 1 to the first. Just going to have an x plus 1 in that denominator. Now this product, or the derivative of that product, requires the product rule. So I'm going to do that separately, and then we'll put it back in line. So I've got the derivative with respect to x of x times x minus 1 to the 3/2. I'm going to think of the x as my first function, and the x minus 1 to the 3/2 is my second, and use the product rule. So we'll have derivative of the first times the second undifferentiated, so you just leave it alone, plus the derivative of the second times the first undifferentiated, so you just leave it alone. And of course, the derivative of x is just 1, and this derivative requires the chain rule. We've got a function nested inside another function. So we take the derivative of the outside function first. The derivative of a function to the 3/2 is 3/2 of that function to the 1 less power. 3/2 minus 1 is 1/2. You put the inside function back inside, and then you multiply by the derivative of the inside. Derivative of the inside in this case is 1. So we just get a 1 there. So the derivative of this product is x minus 1 to the 3/2. And then we've got plus 3/2 times x minus 1 to the 1/2. That's what's going to go there. And then the derivative of that requires the chain rule. Actually, let's do that one real quick. We've got x plus 1 to the 1/2. The derivative of that is, well, the derivative of the outside. Derivative of a function to the 1/2 is 1/2 of that function to the 1 less power. So it'll have 1/2 of the function to the negative 1/2 power. Put the inside function back inside, and then multiply by the derivative of the inside. That's just multiplying by a 1. Okay, so I know what this is. It's down here. I've written it down here, and I know what this is. I just need to substitute that and simplify, and hopefully I'll get the same answer as I got over here. All right. The y prime is x plus 1 to the 1/2. And this derivative of the product is this expression. So I'm going to evaluate, or excuse me, substitute all of this for this. And I'll use some big brackets because this has to distribute to both of these terms. And then we're subtracting x times x minus 1 to the 3/2 times that derivative, which is that 1/2 times x plus 1 to the negative 1/2. And we're dividing all of that by x plus 1 to the first, or just x plus 1. My claim is that this expression is the same as this expression, or alternatively, this simplified version of the expression. If I distribute this to all three of those terms when I differentiated, excuse me, using logarithmic differentiation, I get these expressions after simplification. So I hope that when I'm done with this, I have three terms, and I think I will, because you've got a plus sign here. You're going to have this times this plus this times that. So that's going to be two expressions there minus something else. So you're going to have three terms in the numerator, and divide each of them by x plus 1. So I think I should be able to get it to look like that if I do that algebra. So we're going to have this times this, just distributing, because you've got one term here and another term here, and you want to distribute. Excuse me. Having trouble with my pen. I'm going to distribute to there and to there. So we're going to have x plus 1 to the 1/2 times x minus 1 to the 3/2 as our first term. Then we have plus, we're going to add that. 3/2 of x. And then we have x plus 1 to the 1/2 times x plus 1, or x minus 1 to the 1/2. And then here, there's nothing to distribute, so I'll have minus 1/2 x times x minus 1 to the 3/2 times x plus 1 to the negative 1/2. Now, everything up here is divided by x plus 1. If I have multiple terms, I can divide each of them by x plus 1. So if I had a plus b plus c, all divided by d, well, that's a divided by d plus b divided by d plus c divided by d. Typically, when we're doing arithmetic, we go from this in the other direction. We say, okay, we have a common denominator, just add the numerators. We can also do that in reverse. So if we have a sum of terms in the numerator and one denominator, we can just divide each of them by that denominator. So we're going to take each of these terms and divide by x plus 1. And of course, that's an x plus 1 to the first. And this has an x plus 1 to the 1/2 in the numerator. So if we use that exponent property, x to the n divided by x to the m equals x to the n minus m. And if we use the exponent property, x to the negative n equals 1 divided by x to the positive n, we see that this x plus 1 to the 1/2 divided by x plus 1 to the first can be computed just by subtracting those exponents. We're going to have x plus 1 to the 1/2 minus 1, which is negative 1/2. Now, since it's a negative 1/2, that would be x plus 1 to the positive 1/2 in the denominator. So that first term is going to be x minus 1 to the 3/2. And then this divided by this is going to give me an x plus 1 to the 1/2 in the denominator. And here, so we have something similar, x plus 1 to the 1/2 in the numerator, x plus 1 to the first in the denominator. So when we subtract the exponents, we get x plus 1 to the negative 1/2. So that's going to leave us with an x plus 1 to the positive 1/2 in the denominator. Taking care of those, the x minus 1 to the 1/2 is still there. And this 3/2 x, I'm going to write that as a 3x in the numerator and put that 2 in the denominator. And then this negative 1/2, I'm also going to put the 2 in the denominator and the x there. And the x plus 1s, we can simplify that. The x minus 1 to the 3/2 stays in the numerator. But here, we've got x plus 1 to some power divided by x plus 1 to a different power. So we subtract the exponents. This is x plus 1 to the negative 1/2 minus 1, which is x plus 1 to the negative 3/2. Raising something to the negative 3/2 is like putting it in the denominator with positive 3/2 power. So that is our term there. And the claim is that might be the same as what we got using logarithmic differentiation. So let's look at the derivative using logarithmic differentiation. That we have that term and that term, they're the same. That term and that term are the same, and that term and that term are the same. So yes, we get the same answer. So we might say, okay, what was easier? It's up to you. It's really up to you. Do you like doing the quotient rule with the chain rule in it? And then when you take the derivative of the numerator, do you like using the product rule with the chain rule in order to compute that derivative and then substituting? And then after substituting, like we did here, simplifying. So that's one option. Or, and I prefer this, you could use this beautiful, elegant method of logarithmic differentiation. You say, I don't want to have to take the derivative using the product rule with the quotient rule and the chain rule. Quotient rule first, and then product rule when you take the derivative of the numerator, and chain rule when you take the derivative of the numerator or denominator. You say, I don't want to do that. Rather than that, I'm going to use these beautiful properties of logarithms to say the log of a quotient is this, the log of this minus the log of that. And then I'm going to say, well, the log of the product here can be written this way. And then because of those exponents, I can bring them out front. Now, instead of using the chain rule whenever you have to take the derivative of this, you just have a constant that you're multiplying by the derivative of a logarithm. And derivatives of logarithms are really easy to compute. You just get 1 divided by the inside function, right? The log of a function is 1 over the function. And so I prefer logarithmic differentiation because this is relatively simple. It's very elegant. And then when you take the derivative, you have log of the first is this 1 over x. You bring the constant down. Log of this second expression is log of that second expression times the derivative of the inside. Then you have the negative 1/2 times 1 over the log of the inside function, or 1 divided by the inside function times the derivative of the inside. You get this very simple expression. And then you end up with that simple expression times y, and then y is just a function of x, so you substitute that in. If you distribute, you get the same answer as you would have obtained using the quotient rule with the product rule and the chain rule. I mean, you have to do so much down here. But you get the same answer either way. So I think you might as well use logarithmic differentiation. I think it's a really beautiful, elegant technique. I hope you like it. So anytime you see something like this, somebody asks you to take the derivative of that, say, I don't want to take the derivative of that. I'd much rather take the derivative of this. So I take the derivative of this instead, multiply by y, and then replace the y with that function of x, and we get a really nice simple derivative. I think this process was much more satisfying and pleasing than this process. I mean, it's not rote memorization, it's just not plug and chug. That's not either. What is it called? We're just processing it. We're just going through, just applying those basic rules. This required a little bit of forethought. We said, I noticed that everything would be simpler if I took the log first. So we take the log first. And then don't forget to multiply by y and then substitute that function of x for your y, and you'll be good to go. So that's logarithmic differentiation. I hope you like it.